Welcome, everyone. Welcome to our seminar. Today, we are very happy to have Shirshendu Ganguly from UC Berkeley, and he will tell us about fractal behavior and noise sensitivity in random planar geometry. Thanks, Ganguly.
Yeah, thanks a lot, Shane. And it was great to spend the week at IES. Very sort of exciting to have all these visitors and a lot of discussions. So, so what I'll talk about today is sort of a general sort of area of research that has seen a lot of activity recently around models of random planar geometry. And of course, there are quite a few experts in the audience, and so the plan today is to maybe not focus too much on the proofs, but maybe at least give a flavor of the kind of results that people have been proving, and maybe some indication of what the key ideas behind the proofs are. And yeah, okay. So, and feel free to ask questions, stop me, make comments throughout the talk, and let's see. Okay. All right, so just to get started, so what is sort of sort of maybe the simplest possible model that you can think of random geometry is to take some standard model of geometry, like let's say just Euclidean geometry on Z2, and maybe just perturb it using some IID noise. So for example, yeah, so this is what I'm sort of writing on the slide here. So take Z2. So it has the usual graph metric it comes with. And then for every edge, now let's say you distort it by some random weights. So for each edge, you have some IID, let's say exponentials, which will now denote its edge. So in the usual metric, a particular edge denotes length 1, and now it will have some random length. And that will lead to its own sort of shortest path metric in this random graph. And so as you can see, this is sort of a very simple way to distort the standard Euclidean metric on Z2. And this can also be thought of as a growth model where you just look at metric balls. So you have a random metric, and then let's say fix the origin. Around the origin, you can look at the balls of growing radii, and they are also used to sort of model random growth. And this is what has come to be known as the Richardson model. And so here is sort of a brief illustration. So this is Z2, the edge E has now random length XE. And let's say you are interested in these two vertices marked in red, and you want to look at the shortest path, that's going to be some random path. And this is sort of denoted by the green curve here. And this was first introduced by Hammerstein and Welch in the 60s. And this can be thought of as also a model of fluid flow through a random medium. And for people who are sort of interested in this or want to know at least a little bit about the topic, there's a very nice survey by Offinger, Damron, and Hansen, and which sort of basically covers more or less all of the things that are actually rigorously known and the things that are predicted to be true for this class of models. Any question about the definition? Okay. And so here is sort of a simulation of a metric ball. So you fix that's the origin, and you look at all points at distance at most r, and let r grow to infinity. And the level curves, the curves with the same color denote basically points which are at the same distance from, or roughly the same distance from the origin. And as you can see that if you zoom out, okay, so there is some randomness, of course, but as you zoom out, you see that this is sort of beginning to take some limit shape, and it's known that there's going to be a limiting shape of this metric balls, which will be convex, and that's going to be something that is going to be not universal. So the actual shape will be a function of the distribution that you're using on the edges. But it's known that it's going to be convex. But however, if you now zoom in near the boundary, so the boundary is going to be a random curve. So if you zoom in, it's not going to be a curve, but you can pretend that it's a curve when you sort of try to think of models of this kind. And if you zoom in, like even though the distribution affects the limiting shape, the fluctuation theory is supposed to not depend on the precise details of the distribution. So in some sense, the fluctuation theory should be universal as long as the underlying noise variables are reasonably nice. And as I said, like the metric balls also can be thought of as models of random growth, and this puts FP force passage percolation in a sort of broad class of planar stochastic growth models, which are some of them, which are the class of models which share some sort of key features, which include, like, let's say, slope-dependent growth, some local smoothing with the growth driven by random forces. And under rather general conditions, the fluctuation theory of this kind of models is expected to be driven by sort of universal theory, which has now come to be known as Kardar-Parisi-Zhang theory, or this universality class in general is come to be known as Kardar-Parisi-Zhang universality class. And somehow all of these models should also behave similarly as a canonical sort of growth model given by a stochastic PDE, which is this KP's equation or Kardar-Parisi-Zhang equation. So these are some key features. So H is the height function, which you should think of as your interface. So that grows in time. And the growth rate, which is the left-hand side, is governed by a few things. So here is sort of a smoothening term, which is a Laplacian. Here is sort of the slope-dependent growth in a nonlinear fashion, so gradient square. And here is some randomness which drives the whole process. And so this is sort of a cartoon of what the interface might look like. And it's important that the underlying noise is sort of very heavily decorrelated. So it's like, in this case, it's the space-time white noise, and the correlation structure of the underlying noise affects the eventual outcome of the situation. And okay, so as you can see, like this is a very sort of rough object. So even if this sort of equation makes sense, so gradient of H is sort of, it's hard to define that, but you can still define that in terms of distributions. But then again, making sense of the square of such a thing is very hard. And so it's sort of, it's not quite clear how to make sense of all of this, but it turns out that this can indeed be done. But we will not sort of focus too much on that aspect of things. We'll sort of mostly look at discrete objects and maybe sort of take some continuum limit eventually. So any questions so far about force passage percolation, what the definition is? Okay. And so, okay, so let's go back to this metric example. So what are some of the key observables? So one is you take 2 points x and y, let's say in Z2, and you're interested in, let's say, the new distance between x and y in this new metric. So that's going to be denoted by txy. That sometimes can be also called, that sometimes is also called as the passage time. And then, of course, the other sort of geometric observable of interest is the path itself. So you have 2 points x and y, and you look at the geodesic or the shortest path between x and y, and that's going to be termed gamma of xy, right? Okay, so here is sort of a key feature that will sort of show up many times in this talk. So which is a particular thing that you sort of see in these models of geometry, which you don't see in the Euclidean geometry, is a phenomenon of coalescence. So you see that what are these paths trying to do? So you have, let's say, different endpoint pairs, and you're trying to look at the shortest path between them. So they're all trying to minimize their length given this random noise. And so they're all trying to sort of pass through regions of the noise space where there are atypically low values. And so what that would lead to is that the paths, regardless of where they start from, if they're not too far apart, will sort of eventually sort of meet, share a bunch of their journey, and then eventually again diverge because their endpoints are different. So this is a feature that is sort of course, absent in Euclidean geometry, and it will turn out that much of the recent study focuses on consequences of this behavior. Okay. And okay, so what are some of the questions around the fluctuation theory that you can ask? So one is this random variable, the passage time between x and y, how does it fluctuate, right? And as you can see, like, so it's a minimum of the length over all paths. So now if you fix any path, that of course is the length of the path is just a sum of the random variables along the path. And so that's just a sum of IID random variables. And so that should fluctuate as the square root of the number of variables, or roughly the Euclidean length of the path, the number of edges on the path. But here you're taking a minimum over, let's say, exponentially many paths. So you should expect the fluctuation to be much smaller. So, and this is something that is known as super concentration. So you expect the passage time between x and y to be super concentrated. Okay. Right. And then the next natural question to ask is, what is the fluctuation of the path itself? So you have, let's say, 2 points and the shortest path, although it does not look like this typically. But you can pretend that it's always sort of making progress towards this direction. Then you can, let's say, draw the straight line between these 2 points, and you can ask, like, how much does this random path wander off of the straight line? Okay, so these are some of the more basic questions about this that you can ask. And then you can go into more complex questions. So you can look at the field of distances. So you can vary your x and y and look at the passage time field, and you can ask what is the correlation structure of that set of random variables. Further, you can ask questions about large deviations. So let's say, how do things like the geodesic behave if I tell you that the length of the geodesic is not typical, whether it's too large or too small? Okay, so these are certainly significantly more complicated questions than the questions on the first slide. The first thing that you would like to know are just the fluctuation of the path itself and the length of the path. Okay, the other perspective that is also sort of quite useful is to sort of view force passage percolation as an energy landscape. So you can think of this as an energy landscape indexed by path. So for every path, you can just associate to its length as its energy. And of course, the path has sort of the set of all paths as a non-trivial overlap structure, and you want to understand this energy landscape. And the ground state is the state with the lowest energy. So let's say in this case, it would be simply the geodesic. The geodesic would be the path, which is the shortest length, and in that, and we will term it as the ground state. And we will see that this sort of a perspective is actually quite useful to study some refined properties of the model. So let's look at some other examples where this sort of energy landscape has been studied to some degree, and we will sort of draw some parallel at the end. So another sort of natural example is coming from, let's say, matrices. So let's take a random matrix H. It could be anything, but for the moment, let's just take it to be a standard Gaussian matrix. And given a matrix, it induces an energy field on the sphere of the right dimension. So let's say the matrix is of size n, then you can just look at the sphere of size n-1, meaning like all unit vectors of length n. And then you can just associate to it the energy being the quadratic form induced by that vector. Okay, so that's an energy function on the sphere. And now the ground state could, like because of symmetry, we can just work with the largest. So the ground state would then be sort of the largest eigenvector. So the eigenvector corresponds with the largest eigenvalue. The ground state energy would be simply the largest eigenvalue, right? So this is certainly a much more well-studied model. So here I'm taking the quadratic form on the entire sphere. But it's also sort of interest when you restrict it to the hypercube. So this is I'll not go too much into this, but also a similar sort of a perspective has been taken in models of spin glasses. So here it's again a quadratic form. The only difference is I now take vectors instead of being on the unit sphere. I take vectors on the hypercube. Okay, so I have again a Gaussian matrix, and I look at the energy function induced on the hypercube given by the quadratic form. And the ground state would be simply the vector which maximizes the energy. Okay. And okay, so usually, although things can go wrong in discrete settings, in continuous models, it's usually the case that the ground state would be unique. Like for example, in force passage percolation, if all the edge variables are, let's say, continuous distributions, then it's easy to show that no two paths will have the same length. So in particular, there's going to be a unique path with the smallest length. However, that can go wrong when variables are discrete. But even in the continuous setting, when there is a unique ground state, there could be, and typically for high dimensional models, there are typically many near ground states. So there's going to be one best possible state, but there are going to be many other states that are coming awfully close, right? And this is sort of at least indicated to some degree in this cartoon where this is sort of the best possible state, but then there are many other places where there are deep valleys which are almost close to the deepest valley. Okay, and this phenomenon is known as multiple valleys, and the relative positions of the near ground states have important geometric consequences, as we will see. Okay, so there could be many near ground states, but many of them could actually be quite close to the original ground state. What is of interest is when there are many ground states which are quite far away from the actual ground state. That's sort of the case of interest. And along the slides, you can ask two sample questions. For example, let's say number of near orthogonal almost ground states in spin glass. So there's one ground state which is a spin glass, which there's one ground state in the spin glass case, but now you can look at other vectors which are, let's say, quite far away from the ground state vector, and the far awayness is quantified by this near orthogonality of the vectors. And in the force passage percolation case or related models, you can ask questions about the geodesic. So let's say this one is the geodesic. So what is the probability that there is some other path which is, let's say, essentially disjoint, which is actually whose length is very close to the length of the geodesic? Okay, so this is going to be a counterpart question that you can ask here. And if you're in some continuum setting, then you can, like, let's say, vary these points, and they're going to be varying in the continuum. And then a question of interest becomes, let's say, look at the dimension of pairs of points which actually do admit disjoint geodesics. So of course, given two fixed points, there's going to be unique geodesic. In the discrete case, when you're on Z2, the dimension does not quite make sense. But if you're in some continuum setting, then there will be exceptional points which have disjoint geodesics and which are sort of, and these kind of questions are sort of related to each other. Okay. Any questions? Right. So the distribution of near ground states have interesting fractal properties typically, and an important consequence that we'll also sort of talk quite a bit about is chaos. So what I mean by chaos in this setting, what it will mean is so you have some underlying noise which is driving your model, and let's say you perturb your noise a little bit. So what you would want to know is like whether after a slight amount of perturbation, the geometry of the ground state changes drastically. And that will be what we will term as chaos. And it's not necessary to just perturb the underlying noise. There could be other parameters at play which could also be perturbed. For example, there could be a positive temperature model, in which case the temperature could also be perturbed. But generally, like the point is, like if the landscape is quite intricate, then perturbing tiny bit can cause the ground state to really sort of move about. And this is sort of what I just said. So if you have a landscape which has, let's say, many multiple valleys, this one is a ground state, but these ones come very close. But now you, let's say, perturb the system a little bit, then this one might become the optimal one, and this one might rise up a little bit, which could cause the ground state to jump from here to here. Right. And okay, so I said, like, okay, so perturbing the underlying disorder. What I mean by that? So there could be multiple models of perturbation. So one could be, so suppose in certain cases, it's natural to take the underlying disorder to be Gaussian. And when you do that, then there's a natural stochastic diffusion that you can use to perturb your process, which keeps the Gaussian process stationary. So you can just evolve, let's say your Gaussian process is sigma indexed by some set, and then you can just evolve it along an Einstein-Ludwig process, which is, it's not super important what that is, but it somehow says that it's a stationary process, and the correlation with the original field at time t decays like exponentially in t. So sigma t is the field at time t, sigma is a field at time 0. I should have written a sigma 0 here. And so for any given time, this distributional equality holds that this thing is e power minus t times the original one plus some independent stuff, and you adjust the coefficient here so that stationarity is preserved. So you're gradually evolving your underlying disorder, and you want to understand how much perturbation do you have to introduce into the system. If t is small, this is like close to 1. So you're still highly correlated with the original value, and you want to understand how much perturbation you have to induce into the system to see some meaningful change. But this is not the only model. There could be other models of perturbation, and particularly more suited for discrete settings, which I'll also talk a little bit about. Yeah, so Chatterjee carried out a sort of comprehensive treatment of questions of this kind in various settings, and in particular in 2009 showed the chaotic nature of this eigenvector for this Gaussian matrix. And I'll sort of talk a little bit more about the precise nature of the result. And then more recently, this group of authors, Charles Barthenave, Gabor Lugosi, and Nikita Zhivatovsky, so they basically extended his result for more general Wigner matrices. It turns out that you have a lot of tools in random matrix which allowed them to sort of go beyond Gaussianity. And another sort of model that, like the perturbation model that they were looking at, was not simply an Einstein process, but for a general setting, you can also sort of, let's say, just resample your entries one by one. So you have some large matrix, you have all your entries, which are, let's say, IID up to symmetry, and let's say each entry has an exponential clock, and whenever the clock rings, you resample it. Okay. And then there was also sort of a parallel work ongoing in spin glasses. So after initial work of Chatterjee on spin glasses, subsequent improvements are made by Jing, Eldon, and Zhai, and then more and significantly more refined estimates were obtained by Chen. And the ground state was shown to be chaotic in a large class of models by this group of authors like Chen, Hanshi, and Lermer. And for the subclass of models which are known as even P models, let's not get too much into that, and generalized by Eldon. So there's been a lot of activity in understanding the geometry of the landscape, and the multiple valley phenomena in random matrices, spin glass models, and so on. And this also been sort of quite a sort of deep understanding of sort of dynamical models in percolation. So if you just do critical percolation, let's say on this hexagonal lattice where every side is open or closed with property 1/2 independently, and let's say you're interested in some random variable, let's say whether there's this percolation configuration admits a left to right crossing. So this is the random variable, and this is a Boolean valid random variable. And so in the dynamical model, you port up the underlying disorder. So let's say for every phase, you have a rate 1 clock. Whenever the clock rings, you resample the state of that bit by tossing a fresh coin. And now you want to ask, like, how long do you? So let's say xt is the indicator of the crossing at time t. And let's say how long, and you're interested in how long do you have to wait to sort of essentially decorrelate this random variable. So there's an indicator random variable for all times, and you want to understand how much perturbation you have to introduce into the system so that the status of the crossing is essentially independent of what it was at time 0. And so there's of course a lot of very deep work on this. It was sort of maybe pioneered by the initial work of Benjamin Nicolai and Schramm, and then sort of a very refined understanding was obtained in the later work of Carbon, Pete, and Schramm. And I'll mention some basic thing that appeared here, which will also sort of at least inspire to make use of. So any questions? Okay, and so, but the upshot is that these questions are very far from being answered for FPP. That's sort of the basic message, although these questions all make sense and there's been some impressive progress, but like sharp understanding is sort of significantly far off. And so what we'll do instead is focus on certain variants of FPP, which allow some integrable inputs like connections to random matrices, which allow some important estimates that we can make use of. And so, just to comment that even for such models, only very recent developments allow us to pursue such questions. Like the integrable connections were known for some time, but still, like you have to develop enough geometric understanding to be able to pursue questions of this kind. And so, okay, so just quickly, what is last passage percolation? So it's essentially like FPP. The only difference is you are now orienting the paths, and you're also now maximizing the path length instead of minimizing. So, okay, so I've sort of rotated the lattice for convenience, and now let's say you again have the Z2 lattice in this way, and then for every vortex, now let's say you have some IID weights, and now you consider 2 points X and Y, and you now look at paths which only go up. This is sort of the oriented nature of the model. And for any path, you look at its length, which is the sum of the variables along the path. And now you just maximize overall paths. So LXY will be the maximum length of all oriented paths going between X and Y. So again, as you can see, this is again a ground state type situation. You're looking at some extremal path, but it's also of interest to look at positive temperature models where you put a probability measure on paths. Let's say the probability of a path could be proportional to exponential of its length or something. And so we'll mostly be focusing on the zero temperature model. Okay, so, and the point is like for this model, a special choices of vortex weights. So we had IID weights, which define the model. And so if you now make some special choices, that leads to some algebraic structure, which you can then make use of. So again, like I'll not go too much deep into what the actual connection to algebraic structures is, but in particular, one of the consequences is that when the vortex weights are, let's say, standard exponentials, then this model is related to a bunch of other models, like what is known as a corner growth model. It's naturally sort of admits a growth process, or it's sort of related to a well-known particle system known as totally asymmetric exclusion process. And this is sort of a distributional identity that comes out of all this algebraic structure. So in particular, if you look at, let's say, the passage time between the origin and some point which is vertically above the origin at distance n, that number as a random variable is in distribution exactly equal to the largest eigenvalue of a random matrix. And the matrix here is the Wishart matrix, which is which looks up the kind XX transpose, where X is an IID matrix, and this connection was found by Johansson. But in general, like for many, like for some of this sort of models with particular vortex weights, these kind of distribution items are available where the matrix form might change, but it's still something that is that you can work with, which admits some exact formulas, which allows you to build the fluctuation theory of this guy. And then you can make use of that in your analysis of the percolation model. Okay, so this is the kind of things that we'll sort of be exploiting. Okay, so just quickly, so what is the consequence of all this? So this turns out to be roughly true. So if you're looking at the geodesic, we'll keep calling this path geodesic even though it's length maximizing. So you look at the geodesic between 0, 0 and 0n. So what will turn out to be true is that ln will be, let's say, the length of this path. So using the asymptotics of this largest eigenvalue, one can show that ln will be like growing linearly then with the constant 4 in the exponential case, and its fluctuation is going to be like n to the 1/3. So recall that, as I said, like for any given path, the length is just a sum of n independent random variables. So it has square root n fluctuation, and this shows that indeed the fluctuation over the maximum of all paths is significantly smaller. And it's also known that if you now look at this order 1 object, when you center and scale properly, that has a distribution limit which is converging to what is known as this Parisi-Zhang distribution. So again, I'll not go too much into that. And the other more geometric consequence is the fact that if you look at this path, the fluctuation from the straight line is of order n to the 2/3. Okay. And so these are sort of exponents that come out, which is supposed to be true in all of these models, but are provable only in these cases where we use some matrix connections. Okay. And okay, so as I said at the beginning, sometimes it will be convenient to, instead of working with individual models, to work with a continuum, which is a universal scaling limit and supposed to be the limit of all of these models, and actually proves to be the limit for this integrable models, which is known as this Fractal landscape, which is constructed in, I think, 2018 and 19 by Dalvan, Ottman, and Barak. Okay, and so this will be a limiting random energy field. So you should think of this as a scaling limit of this metric spaces. So what is it actually? So it's some random function from R to the 4 with an arrow, which is not super important maybe to focus on. So it takes as input 4 points, x, s, y, t. So you should think of x, s as a point and y, t as another point, and you're going between x, s, and y, t. And s is less than t, and this is sort of the oriented nature of the model. And this should be thought of as a scaled distance between these 2 points. Okay. And it satisfies some scale invariance properties, like Brownian motion is invariant under diffusive scaling. Here, the exponents that you should scale by are this 2/3 and 1/3. Again, it's not super important to focus on this. The point is this satisfies some scale invariance properties given by exponents that we were seeing on this previous slide of 1/3 and 2/3. Okay. And just one more point about this is, like, if you now, let's say, look at the marginal, so you have this landscape which looks at all distances between pairs of points x, s, and y, t. But now suppose you fix your initial state to be the origin, and you fix your and you vary your final state to be on this horizontal line at height 1. That sort of curves out a random function, and that random function globally looks like a parabola, and this has to do with the convexity of this distance functions, and with some random fluctuation on top of that. And the fluctuation is given by what is known as the AV2 process. So this is a stationary process which is determinantal. And the 1-point distribution is the Parisi-Zhang distribution. So the kind of scaling limits that we were seeing of the distance scale converging to a Parisi-Zhang distribution leads to the 1-point distribution itself on this field being Parisi-Zhang. Okay. And okay, so just to again repeat the coalescence picture. So given into fixed endpoints x, s, and y, t, the geodesic is typically unique. So the geodesic actually does make sense also in the landscape, which is not entirely a trivial statement. And it also turns out, because of this transversal fluctuation of 2/3, that these geodesics are 2/3 minus Holder regular. So these are random curves which are unique for given fixed points, which are 2/3 regular. And when you sort of take 2 points nearby, they will typically meet. Okay, so this is the coalescence picture that I was alluding to. And as I said, like in this case, you're away from the discrete setting, so you have uncountably many endpoint pairs that you can sort of look at, and on account of them being uncountably many of them, so it turns out that there will be exceptional points where the uniqueness thing will be violated. So you will have endpoint pairs where you will have non-unique geodesics between them, and they will also not coalesce. And so in a couple of papers with Basu and Hammond and Bates and Hammond, we looked at such situations. So let's say you fix 2 points here, -1 and 1, and let's say you vary your point X upstairs at height 1 for the moment, and you can ask, like, what is the set of X where you see a situation like this, So for every X, typically, if you look at the geodesics going down to -1 and 1, they will initially coalesce and then they will bifurcate. But you could have exceptional points where they don't meet at all, except for the starting point. And across these papers, we show that the Hausser dimension of the set of such points is 1/2. Actually, we also looked at a situation like this, where you now vary both these pairs of points as a subset of R2, and look at the set where you admit disjoint geodesics. And that also turns out to have Hausser dimension 1/2. So is the sort of statement roughly clear? Okay. Okay, so NC for non-coalescing. This NC is a random fractal subset of dimension 1/2, and I can try to ask more things about it. And so, for example, you can first start by asking what is a canonical random set which has fractal dimension 1/2. And of course, the first thing that comes to mind is the zero set of Brownian motion. So the zero set is just simple Brownian motion from on the real line. The set of times where it's at 0 will be a 1/2 dimensional set. And it actually also supports a natural measure, which is the Brownian local time. So there are multiple ways of defining this. One way is to just look at it as the density of the occupation measure. So you run Brownian motion. Let's say you run it from time 0 to t, and then you look at the time it spends near the origin. So look at the time it spends between plus minus epsilon. Okay, so that's sort of the occupation measure of a cylinder of width epsilon. And now you divide by epsilon and then send epsilon to 0. It turns out that this will have a limit. And this is what is known as Brownian local time. And you can show that this is supported on the zero set. And so in a later work with Milind Hegde, who's now postdoc at Columbia, and also it was separately shown by Duncan Dobbin, we showed that this sort of set of points which has non-coalescence, which has fractal dimension 1/2, actually separates a natural measure, which is absolutely continuous to Brownian local time. Okay, and in particular, if you look at this random measure supported on this random set, if you look at some local limits of that, this will be exactly Brownian local time. Okay, and so this is not a very precise statement, but the sort of general message is that this thing does look like Brownian local time, or let's say the set of points which has non-coalescence does look like the zero set of a Brownian motion. Any questions? Okay, and so let me just quickly indicate where the Brownian behavior stems from. And this was the thing that I was showing you earlier. So the ARE2 process. So recall that the ARE2 process came from the passage time profile. So if you fix your origin, and let's say look at the other point varying on this line, and if you look at the different distance profile, so that would be some globally parabolic thing with some local fluctuations. And I said that that would be a determinable process. So it turns out that this thing is itself a locally Brownian process. So the 1-point distribution is Tracy Widom, but if you now look at the increment of this process, that will actually be very strongly related to Brownian motion. It is sort of significantly, I mean, like there are sort of a lot of recent results which tries to compare this process to Brownian motion with very strong estimates on their densities. Okay, so this is where the Brownian-ness comes in, and this actually does lead to many sort of objects in this model which are comparable to Brownian statistics. Okay, and this leads to this 1/2 type dimension. Yeah, so one particular work work of Calvert, Hammond, and Hickory, and then more recently by Taubman, establishes very strong comparison estimates with Brownian motion. Okay, so but like recall that the Brownianness is only true when you vary it in the spatial direction. Okay, so we have two directions. So let's call the horizontal direction as spatial and the vertical direction as temporal. So the Brownianness of the horizontal direction actually makes some of this analysis somewhat easy and leads you to comparing it with Brownian motion and whatnot. However, you can also ask similar questions about observables, but when things are also varying in time. And that actually makes it significantly trickier because you don't have the Brownianness in the temporal direction. So for example, if you ask a question like this, like what are the set of all points xs and yt where t and s are different, which admit disjoint geodesics to points of this kind? Or you can just fix some vertical axis and you can look at all points on this vertical axis which admit disjoint geodesics. And so you don't have this sort of luxury of comparing with Brownian type objects in this sort of a situation, which makes them significantly harder to work with or analyze. Okay. All right. So this was sort of addressed in a recent paper with Lingfu-Zhang, where we showed that the Hausdorff dimension of the set of all points of this kind is 2/3, and when you sort of don't restrict them to a vertical line and vary it in space, that's 5/3. So 5/3 is essentially this plus 1. So this is sort of and recall that when we instead had the horizontal line, this was 1/2. So the vertical line, the dimension is different, and this is because that the behavior of the process in the temporal direction has a different fluctuation theory. So if you look at the passage time profile in this direction, that's a Brownian-like process. That's 1/2 Holder regular, whereas if you do it in the vertical direction, that's 1/3 Holder regular, and so that sort of features into the proof. Okay, so questions? Okay, so I'll not go into the proofs, but I just want to mention one of the key ingredients is to construct the notion of a geodesic local time. So we said we just talked about Brownian local time, which is a measure which is supported on the zero set of Brownian motion. So now you can look at a geodesic. Let's say in this case, it's an infinite geodesic. So I've not quite defined what that is, but it's some semi-infinite object which starts from the origin and goes off in the vertical direction. And so what turns out to be important for this previous statement that I just stated is to construct a measure which is basically the times at which this hits the vertical line. And recall that Brownian motion, the reason why the zero set is 1/2 dimensional for Brownian motion is because Brownian motion itself is 1/2 Holder regular with a minus, and the half in the zero set is 1 minus 1/2. And so I just commented a few slides back that the geodesic itself is 2/3 Holder regular, and that naturally leads you to speculate that the zero set should be 1 minus 2/3, which is a 1/3 object. So the zero set indeed is 1/3 dimensional, and it's and you can actually construct a measure supported on that. And this was sort of important to get those Hausdorff dimension results in the previous slide. Because so usually a way to show lower bound for Hausdorff dimension is to construct a measure with the right Holder regularity properties, and we use the geodesic local time along with other things to construct such measures. Okay. All right. So just a few comments. The construction of Brownian local time relies on the Markovian nature of Brownian motion, whereas geodesics are highly sort of non-Markovian objects. So some of the key things that go into the construction of the geodesic local time are things like translation invariance and coalescence, kind of things, because you cannot do them sort of in a local way. Okay, and then more recently, Manan has computed some disjointness of geodesic exponents in some related settings. And very recently, Dalborn has sort of essentially classified all possible geodesic intersection patterns and computed their dimensions in a slightly sort of altered metric given by the KPZ exponents. Okay, so there's a lot of activity recently in this sort of direction. Okay, good. So So we have so far seen various results about determinants of geodesics and associated fractal measures. And the results themselves, as well as the proof ideas, actually provided some insight into the energy landscape induced by last passage percolation. And this will actually allow us to sort of attack this problem of chaos in this setting. So how chaotic is the energy landscape or the geodesic itself? So as I said, so the last 2 decades have witnessed substantial activity in the study of noise sensitivity for probabilistic models. And perhaps most notably for planar critical percolation in the sort of work of Benjamin Nicola and Schramm, and then Carbon-Petty and Schramm that I was mentioning. And for polymer models or this sort of geodesic type models, actually there has been heuristic discussions in the sort of non-rigorous literature, which we found to be sort of going back to the early 2000s. And only now some of our mathematical understanding is rich enough to sort of actually try to make some of these things rigorous. And so I'll say what the results are and maybe how one might approach them. But let's go back to the random matrix question for one more time. So let's say at this point, let's say this is a GUE matrix. So symmetric or maybe Hermitian, and then entries are IID GUE up to this constraint. And so now you can sort of port up these entries as entries evolving as standard OU processes. Okay, so these are complex Gaussian, they evolve into everything, real part, imaginary part, they're all independent. So they all evolve as IID OU processes. And it's sort of somewhat nice because here the eigenvalues of this random matrix evolve as a Dyson-Brownian motion. I mean, a stationary version of it. So the standard thing is if you have a matrix whose entries evolve as Brownian motion, then its eigenvalues will evolve as Dyson-Brownian motion. And this is sort of a stationary version of that. And you can ask questions about this. So again, if you talk about the ground state or the ground state energy, so you can talk about the largest eigenvalue. So lambda 1t is the largest eigenvalue at time t. V1 is the corresponding eigenvector. And so you can ask things about how correlated is the eigenvalue at time 0 and at time t, and how close are the eigenvectors at time 0 and time t. Okay. And on the counterpart side of LPP, so there are different things that you can do. Let's say if you have a discrete model, then what you can do is you can have every vortex, and then you can let's say if there are sort of, let's say, non-Gaussian or whatever, regardless of whether they're Gaussians or non-Gaussians, you can do a discrete update where you again resample every vortex at rate 1 independently, and just to sort of set up some notation again, gamma nt and lnt. Let's say this is the geodesic at time t, and this is the passage time at time t. Okay, and so the noise sensitivity question is how long does it take, or how large t must be for the passage time to essentially be independent, and the chaos question is when does the geodesic start looking different? So gamma n0 is, let's say, so this is a geodesic at time 0, this is a geodesic at time t. So when t is not too large, you will have a lot of overlap between the geodesics. But then when t is large enough, the geodesic might start looking quite different. And how do you quantify that? So these are like discrete paths for the moment, let's say. So they are all discrete paths which have n vortices in them, or maybe 2n. Doesn't matter too much, but then yeah, I think it's n the way I set it up. And now you can look at the number of vortices that they share. So you can look at their intersection. So that's the number between 0 and n, and you can quantify how similar or how dissimilar they are by looking at this observable. Okay, so at time 0, it's of course n, and then it's a gradually so it's decreases, and then you want to understand when does it become little of 1. Any questions about the setup? Okay. And so in a paper with Alan Hammond, so we did not quite study the discrete model. So we were looking at a semi-discrete Gaussian model, and we were perturbing it with OU updates. So again, the Gaussian process was evolving as a non-linear process. So what we showed was when t is smaller than the system size is n. So what we showed was when t is smaller than n to the minus 1/3 with some subpolynomial corrections, the overlap between the two geodesics is linear in n with high probability. And when t is significantly bigger than n to the minus 1/3, the overlap becomes microscopic at scale n. So this is little of n. So it goes from theta n to little of n as t crosses this critical window of size n to the minus 1/3. Okay. Right. Yeah. So this result you can call subcritical stability. So the geodesic is somewhat stable when t is not too large, and the geodesic is chaotic when t becomes bigger than (10⁻⁻⁴). Okay, so actually, as I said, like so the model that we studied was a different model, and this is known as Brownian last passage percolation. And so what it does is, so instead of having, okay, so I cannot, yeah, so basically, oops. Yeah, so essentially what it does is, so this is, so what we're looking at was discrete models like this kind. So you had vortices, and then you were looking at paths of this kind. So in the Brownian last passage setting, what you have is you essentially take a limit of this guy in this direction. So basically, instead of having discrete vortices, you have a copy of real line for each height. So you have, let's say, a copy of a bunch of real lines. This is 0, 0. This is n. And now for each line, you have some independent, let's say, Brownian motion. Okay, and now if you look at a path which goes like this, let's say it's spends some time at the first level, then jumps, spend some time at the second level, and so on. That for any such path, the length would be simply the sum of the Brownian increments. So you take this Brownian motion, look at the value here minus the value here. So that's the increment that it picks up. And then you do that for every level, and then you add it up. Okay, so this is like the discrete setting, but instead of summing the vortices on the path, you essentially take the Brownian integral, take the Brownian increment along that segment. Okay, so is the definition clear? Okay, and so it turns out that this has a sort of very nice integrable structure. In particular, if you look at the last passage value from 0, 0 to, so if instead of nn you had some xn, and then you varied your x, so that would be some random curve as x varies, that would be exactly in distribution the top line of a Dyson-Brownian motion of size n. Okay, so that is something that you can that allows you to get the optimal fluctuation estimates for this model. So this is sort of the integrable structure that this thing possesses. So okay. Okay, so here is some simulation. I think I don't remember exactly what the underlying noise was. Maybe, yeah. So this is saying this is showing some subcritical situation where you have some significant overlap, although there is a non-trivial excursion, it seems. But here it's mostly disjoint in the subcritical case. Okay, so recall, so you have a system of size n. And what the result indicated was that the jump from stability to chaos happens at scale n⁻⁻⁴. So you can now ask, like, why is n⁻⁻⁴ the right location? And this location was indeed predicted in the physics literature in this paper, which we could trace back to. So Da Silver and Bouchard in 2004. But the argument there is a bit faulty. So but they still come up with the right location for the transition. And let's sort of see. So this is sort of not. So this is much easier to see for the random matrix case. So recall in the random matrix case, suppose you have some initial value of the matrix, and you get this eigenvalue process λ1 through λn. And now, as your entries are doing constant orbit processes, the eigenvalues themselves are doing stationary Dyson-Brownian motion, right? Now it turns out that the fluctuation of the largest eigenvalue, if you normalize things correctly, so that these are order rate 1 Brownian motions or something. And the fluctuation of the largest eigenvalue, so the largest eigenvalue will look like some constant, let's say 2. And then it will have some fluctuation, which is like n⁻⁻⁴. Okay. Now these are Brownian motions conditioned to, let's say, not intersect each other. But locally will, so this n⁻⁻⁴ also turns out to be the typical gap between the edge eigenvalues. Okay. So locally it will not feel the effect of this non-intersection, at least for some time. So I can pretend that the top guy is just in Brownian motion. And now you see that at time n⁻⁻⁴ is precisely when the fluctuation of this Brownian motion matches the original fluctuation of the eigenvalue n⁻⁻⁴. And which is when the new value should sort of start decorrelating with the original value. at scale into the -1/6, right? So at least in the matrix setting, it's sort of not very difficult to sort of predict what the location for this transition to happen is. And however, like as I said, like in the random matrix, many more tools are available. So this paper of Bordenave, Lugosi, and Shvatowski actually does prove the same transition even for general Wigner models, like where the distributions are not Gaussian and they don't have any sort of DPM type structure, but they can really rely on some very precise resolvent estimates to really sort of prove the same result. Okay, so, and right, as I said, so this was for GUE case, it was first shown by Chatterjee, this location. I'm like, he showed only one part of the result. He showed that if time is bigger than n to the -1/3, then the eigenvector is chaotic. So the new eigenvector overlaps very little with the original eigenvector when t is large. He did not show that for small t, they overlap quite a bit. However, this group of people prove both sides of the transition, and in a significantly more general setting, and for general perturbation models where you do either OU or do discrete updates. Okay, so let's see why this might be the right location for last passage percolation. So let's say this is the geodesic between 0, 0, and 0n. Okay, so by time t, if you evolve, okay, so let's again for the heuristic purpose, let's just do the discrete update. So by time t, the number of bits that you have updated, each bit is updated with probability proportional to t. So if a path has length n, then the number of bits updated on the path is roughly nt. Okay, so you see that. Okay, so recall that the passage time had fluctuation, which is n to the 1/3. So ln was something like, maybe for the exponential model, like 4n plus order n to the 1/3. Right now, let's see how the process evolves. So initially you have some geodesic, and let's say at time t, some bits are refreshed. Okay, now the geodesic is going through atypically large values, right? Geodesic is trying to maximize its length, so it's going through atypically large values. So when I sort of replace a value on the geodesic by some typical value, I'm resampling it, so I'm replacing it by a completely fresh bit. The value of the new random variable should be smaller than the value that it originally had on the geodesic. So every time I'm refreshing a value on the geodesic, the energy of that path itself is sort of going down linearly in some sense. It has a very large negative drift. Okay, so let's look at a slightly earlier time. So let's say t is n to the -2/3 initially, okay, or something slightly smaller than that. In that case, the number of bits that you have updated on the path is nt, which is like n to the 1/3. Or let's say t is little of n to the -2/3, so slightly smaller than n to the -2/3. Then the number of bits that you have updated on the path is little of n to the 1/3. And so the energy of the path, although it's sort of going down, energy of this particular path, although it's sort of going down with negative drift, it's still sort of competitive up to time t equal to n to the -2/3, because this is still sort of not, the negative fall is still not matching up to the typical fluctuation of the system. However, the claim is that the transition happens much later. So by time t equal to n to the -1/3, which is the claimed location for transition, the number of bits that you've updated on the path is n to the 2/3. Right? N times t is n to the 2/3. And so you see that this path has become completely hopeless at this point. So the negative drift has made it completely uncompetitive at this point. But what the system will try to do is it will try to locally make up for this loss. So I'm like, although this is the best path, locally there will be sort of reasonably good paths. So it will try to sort of make up for this loss by these local reroutings. And you can expect that because of the separation of the location of the updates, these local reroutings are somewhat happening in an independent fashion. This is all very heuristic at this point. And so which means that the net change due to this local reroutings has a cancellation, and so which is governed by some central limit theorem type effect. So you have n to the 2/3 many locations. They're all sort of behaving independently in this rerouting. So the net change is square root of n to the 2/3, which is n to the 1/3, which is matching the actual fluctuation of the system. So this sort of, at least from this sort of a completely hand wavy type argument, one can maybe expect that this is the right location for the transition to happen. Okay, but this is all very sort of non-rigorous at this point. So 5 minutes or 5 minutes. Yeah. Okay, so proof takes a rather different route. So relying on probability of existence of near geodesics. So we'll see how that sort of features in. But the first key thing is some harmonic analytic tools for LPP. So this was also like we will see is like so when you try to study noise sensitivity, Fourier analysis is sort of a natural thing that comes up. And so this was also sort of very, very crucial in the study of critical percolation. And so particularly this work of GPS really sort of understood the spectrum or the Fourier expansion of critical percolation very precisely. And as we'll see in the next slide, why sort of harmonic analysis sort of comes up naturally in such questions, in the study of such questions. So again, it's sort of the cleanness in the Boolean setting. So I'm going back and forth between different setups, but so for us, the underlying setup is Gaussian, but for the moment, let's just look at a Boolean setting. So you have some function, let's say, which is Boolean from the hypercube to again, -1, 1. So you're outputting some bit. And so suppose, so this is the uniform measure. And so this is a random function. So this can be thought of as a random variable when you put the uniform measure on the hypercube. And now what you can do, so you have some vector, you evaluate the function, and now you can sort of, again, try to update every bit independently. And you can ask, like, when does the value of the function essentially decorrelate? This is essentially the critical percolation setup, right? Because somehow I was looking at the indicator whether there was a crossing or not. And my underlying space was given by this open or closed faces, which is a hypercube, right? And so if you update your bits at rate 1, the correlation value of f at the original time, at the initial time, and at time t will have some nice expression in terms of the Fourier expansion. So let's just quickly review that. So the Fourier basis in the hypercube is given by polynomials of this kind. So they're indexed by all subsets of bits. So there are n bits in total. So you look at all subsets of bits. For any such subset, you look at a function of this kind, which is just the product of the bits in that subset. And then f admits, so there are 2 to the n many such functions, chi s, and this is a vector space of dimension 2 to the n. So this will be all orthonormal to each other, and so any function will admit an expansion in these spaces. And what turns out to be true is that the correlation between the value of the function at time 0 and time t is exactly summation of alpha squared times e power minus st. So s is the size. S is sort of indexing the Fourier eigenfunctions, and here we are looking at the size. So somehow the point is, like, the larger the size set S is, the more frequent, the higher the Fourier mode is. So you see that this is a correlation, and summation alpha square is essentially the variance of the function. Okay, so you see that if all of your Fourier mass, so you can think of this as the Fourier mass. So if all of your Fourier mass is concentrated on large values of S, then a tiny amount of t will make it decorrelate. Okay, so somehow this is like, if your function is supported on the high Fourier modes, it will be more noise sensitive. It's basically the upshot. Okay. Right. So again, you can do a Gaussian counterpart of that. That's not super difficult. And so Chatterjee indeed sort of set up a comprehensive, like sort of a unifying framework, which treated this random matrix question and the spin glasses and related models. And the point is, like, instead of the eigenfunctions that I just indicated, you just do the Hermite polynomial expansion, which forms the Fourier eigenfunctions in the Gaussian space. And actually using this harmonic analytic input, you get harmonic analytic framework, you get 2 inputs. So one is this local subcritical stability of the weight. So correlation of the passage time at time 0 and passage time at time t is quite close to 1 when t is small, is a reasonably straightforward consequence of this Fourier analysis. And on the counterpart, it also follows that the geodesic is chaotic at large times. So when t is bigger than n to the -1/3, the overlap is little of n. Okay, so these are reasonably sort of straightforward consequences of this general Fourier theory, and which was also sort of used by Chatterjee in the study of random matrices and similar models. Okay, so it means that it remains to prove the other direction. It remains to prove, let's say, okay, so we claim that this thing transitions from stability to chaos. So this already proves chaos for large times. So the remaining part is to prove stability for small times. So you want to prove that if t is smaller than n to the -1/3, then the geodesics are not too different. Okay, so the main point is, okay, so we are having this noise space, one for each time slice. and sort of difficult to compare things across times. So this energy landscape understanding is for a static time, right? So you fix a time and you have some understanding. So somehow if you can reduce this dynamical question to a static problem, then it's sort of somewhat maybe more convenient. And so that's what we do. So suppose you have a geodesic at time 0 and geodesic at time t. So a big part of the proof involves the construction of a shadow of the geodesic at time t at time 0. So you have a path at time t, which is the optimal path. You want to create a shadow of that at time 0, which preserves most of its properties. And the construction is quite complicated, so I won't go into that. And this is sort of a cartoon. So let's say the red path is the geodesic at time 0, the blue path is the geodesic at time t, and the green path is some proxy for the blue path, but now lives at time 0. Okay, and the shadow, sort of the things that you demand from the shadow is that the overlap structure, the excursion structure between the blue and the red path should be similar to the excursion structure of the green and the red path, so that geometrically they look the same compared to the relative to the red path. And also that their weights are not too different. The length of the green path and the length of the blue path are not too different. So these are essentially at a high level the kind of things that you want to have in your proxy. And so just let's do a try case. So suppose I want to rule out a figure like, so I want to prove stability. So I want to prove that the blue path is actually quite close to the red path. So look at the extreme case where the blue path is very, very disjoint from the red path, let's say. Suppose I want to rule that out. That's just the most basic case that you might want to rule out first. So the proxy construction tells you that there is a green path, which is like now living on time 0, which looks like the blue path. So in particular, it's very away from the red path. And its length is close to the blue path. But by this Fourier analysis input, we know that the weight of the blue path and the weight of the red path, they're quite close to each other. So the weight is stable for small times. So if you fit that in, all that implies is that now you have a green path and red path both at time 0. The red path is a geodesic, and the green path is a near geodesic. And so you want to prove that this is unlikely. And so this can actually be reduced to a question about a Brownian motion, again using spatial Brownian properties of the Brownian motion. What is the probability that so it basically boils down to saying that the Brownian motion has maxima here and a near maxima here. And that's a Brownian computation that you can show it sort of has small probability. But of course, this is sort of a very tight case. The actual thing involves sort of considering multiple scales. You can have different excursion geometry and handling all of that. But essentially, the rough upshot is that you want to reduce it to a static object and then want to use static near geodesic probabilities to handle those cases. Okay. Just to summarize, so recent developments are mostly done. So recent developments allow us to gain some understanding of the metric structure, in particular pertaining to fractal behavior and noise sensitivity. And many natural problems remain open. So one is to prove the energy decorrelation beyond this time, so prove the energy counterpart of this result. The other is sort of quite interesting, is the study of critical behavior, which is open even for random matrices. So this I find, this I think should be maybe doable and maybe quite interesting, is to understand the overlap of the eigenvector in the critical window for the random matrix set case. And the third one is like, how does the Fourier expansion of LPP behave? So, okay, this is a big question at this point, but let me just expand a little bit on that. So there is a natural measure called the spectral sample defined by the Fourier coefficients. So I sort of, I don't have too much time now, but so in the Boolean case, you recall that we had this expansion. And so S were subsets of bits, right? So every eigenfunction is indexed by a subset of bits. So now you can put a probability measure on the subset of bits. So this probability measure is proportional to alpha square. So the Fourier coefficient square can be used to define a probability measure. And it turns out to be, as we saw, the correlation between the value at time 0 and time t is exactly the exponential moment of the spectral sample size. And so for critical percolation, one of the key things that was used is that the size of the spectral sample was somewhat concentrated. So that was one of the key things that they proved, and then they used that to understand the noise sensitivity properties. In the LPP case, it seems that the presence of near geodesics, although that's a small probability event, that will ruin this concentration and it will tend to make this more heavy-tailed, the spectral sample. And so just understanding the tail behavior of this Fourier expansion is an interesting problem by itself. And then at the last slide is like, you can also go beyond zero temperature and talk about positive temperature models. So instead of picking the extremal path, you can put a probability measure on paths as, let's say, exponential of the length or something. Particularly important model is what is known as the continuum directed random polymer. whose free energy is described by the KP's equation. And so you can, so this also is supposed to so exhibit a lot of sort of nice properties. And so in ongoing work with Agarwal, we prove a structure theorem for this Gibbs measure, understanding its excursion structure and the critical exponents that come out of that. Yeah, so I'll stop here. Thanks.
Any questions for Shirshendu? Sorry.
You had some comments about the spectral structure. I did not quite get that.
Yeah, so like, right, so
what is it?
yeah, so exactly. So I'm like in the Boolean case, it's the cleanest. So it's some, so you have, let's say, some subset of bits. So every Aij is independent, let's say, Bernoulli. Okay. So now you can, so whatever function you care about, so that can be thought of as a function from the hypercube. N or n squared, depending on what your size is, to let's say even -1,1. In our case, it's not
the spectral decomposition.
Yeah, but the point is like, so given the spectral decomposition, you have some set which is a random set now whose probability is given by the spectral expansion of f. So it's like, so every function f induces a probability measure on subset of bits. And now you want to understand how, so that's a probability measure that has a priori nothing to do with the original probability measure, but there are some connections. So for example, if you like, there is this notion of pivotal points, like for example, in the original measure, the points that are quite important for the value of f actually have some interpretation in the Fourier side as well. And so let's say if, in percolation, there are all these sort of pivotal points of related to this crossing events. And so it turns out that the spectral sample, the size of the spectral sample, at least in expectation, is close to is actually equal to the expectation of the pivotal point. So if you understand the spectral sample well, you have some understanding of what the primal space is as well. But it turns out that, and in particularly in relation to this noise sensitivity, there is a direct connection. So if you have some understanding of the concentration properties of S, then you essentially know how the correlation decays. And so somehow that makes it interesting to understand what the typical distribution of this number is. And in percolation, it turns out to be somewhat concentrated. By that, I mean, let's say the second moment of this random variable is roughly the force moment squared, okay? Let's say in percolation, something like this is true. Whereas in this sort of model that I just described, it turns out to not be true because of some rare events that screws up the second moment.
So they understand that the concept refers to the distribution of S within the
along the Fourier spectrum. Yeah,
the power spectrum.
Yeah, exactly. Yeah,
because
so
the power spectrum.
Yeah, if you understand that well enough, then you have a very good handle on the noise sensitive properties of the random variable.
Just double check. So your model at t equal to 0, it is this Brownian last passage.
Sorry, what's that?
So your model at t equal to 0.
Yeah. So exactly. So I said
dynamic is
yes. I said whenever there's some Gaussian process, you can always do an OU, regardless of whether the Gaussian process is a single Gaussian or some complicated abstract Gaussian. So you can actually evolve the whole Brownian motion along an OU process. So you have all this bunch of independent Brownian motions at time 0, and then each of them evolve independently as OU processes, and that's your noise at time t.
I see. And this Brownian as infinity also convert to this directed landscape.
So the passage time profile, but that is true also for discrete models. It's known that even for the discrete models, if you scale things properly, they will converge to the landscape.
Do you also have a continuum dynamic?
Yeah, so that's actually that should have been that should have been a question on the slide. So it's sort of will be quite interesting and actually might be also of importance in relation to this correlation question to understand whether there's a scaling limit of this dynamics on the Airy-Line ensemble.
Yeah, that would be very interesting.
Yeah. So there are some intermediate questions of sort of same flavor. Like for example, you can do it not at the, so LPP seems a bit harder than random matrix. So in random matrix, if you take the entries and evolve as Brownian motions, you get DBM, Dyson Brownian motion. And if you take the edge scaling limit, you get the Airy-Line ensemble. But now instead of taking the entries to be Brownian motion, you can take them to be like, let's say something like the Brownian sheet. So you have some Brownian motion, and then let's say it also evolves in the other direction. And so now you have a space-time field of eigenvalues whose every sort of time slice is a deep Dyson Brownian motion. Now you can ask, and whose edge limit is also like the area line ensemble. But now you can ask whether this space-time thing has some scaling limit at the edge. And that would be another way to construct some dynamics on the area line ensemble. So maybe it's easier to do it on the random matrix side first to at least construct some object on the area line ensemble, which is stationary and has this sort of local Brownian diagram.
Any other questions? Okay, if there's no question, let's send our speaker.